Okay, you should be good to go, Peter. Thank you very much.
Okay, great. Hi, my name is Pete, and I'm a programmer for CC3D. I've been working with this group for about a year now and joined last year after the hackathon. But nowadays, I'm also a full-time software developer for Salesforce, and that takes up most of my time. So I appreciate your patience with, me coming in just at this part of the day, and it's going to be a fun module. So we have quite a bit on the agenda for today. These are mostly going to be what I call our tools for success. There's a lot of miscellaneous features here, things about visualizations, using some of the latest features like a demo browser, and even installing the VSCode plugin. So we're going to be working with the demos a lot today, the ones that are built into Compiso. If you don't have these set up on your machine already, maybe if you installed with Miniconda, you can actually download them from the Git repository, place them onto your machine, and go into the configuration menu of the player and specify the workspace directory, or excuse me, the demos directory manually. I'll only show some of these instructions very briefly, so you probably already know. You can just look in the student materials folder if you want to see the slide longer. So we are here at the end of the day, the schedule. And next up is the VS Code plugin. You don't need the plugin, but it is a recent feature and it allows you to insert the snippets into what could be potentially your favorite IDE. So just like Twitter, you have all the snippets in a menu on the side. And based on which file you're editing at any given time, whether it's XML, C++, or Python, you're then able to copy one of those over. So in order to install that plugin, you're going to open up VS Code. You click the extensions menu, which is the building blocks icon. And then you're going to search for CompiSol3D. Once it comes up, there's a download button. So I'll give a minute for if anyone wants to do that.
So I've put this in the chat, but just in case anybody missed, this particular part of the tutorial can be considered optional. VS Code, you do not need VS Code to use CompiCell, so if you're not planning on using VS Code or if you don't use VS Code, you don't necessarily have to do this part. But VS Code is a very popular code editor. So if you do use it, having the plugin installed when you do your CompiCell work is useful.
Yep, and to add to that, this is something I implemented in response to user feedback. A lot of people are just already familiar with VS Code, so they prefer that. But if you're a beginner with both of these, then Twidit is a great option because it has so many features built in already. We'll talk about parameter scans later on in the week, but the developer zone, we may not, and that's basically like a way to get started with developing your own C++ modules for CompiCell. So you may already be familiar with a workflow for CompiCell, but since this VS Code plugin is pretty bare bones, it's very new, you want to create your simulation project in Twidit first, then open it up in VS Code and go back and forth between playing and editing your code as you normally would. So we're going to kick off our first demo here. This one is largely going to be review. And it's all about iterating through cell neighbors. And you can find the source code in our Google Drive folder under cell neighbors. So let's open up that separables file. The first one is very similar to you, just iterating through all the cells in a cell list. Once you have the Python file open, just scroll down in the VS Code menu if you so choose. Go down to Visit, which is at the very bottom, and click All Cells. and that'll insert this very snippet. So you can choose to either double click it or click the blue arrow. So besides that, you can also iterate through these cells according to their type, which when you do so, you call cell list by type, and you must capitalize the type name. So in my XML file, they're actually just called Pascal case, type A and type B. There are other ways to do this, of course, for example, with Python generators, which would look something like this, cell for cell in cell list, and you can apply a filter while you're at it. I won't spend too much time on the concept since this is essentially the equivalent of the above. The main thing you want to care about instead is being able to check the surface when you're looking at cell neighbors. So let's say I grab an arbitrary cell, let's say number 12, and then you can print the surface very easily using a built-in property. But once you iterate through the cell neighbors, which is the visit cell neighbors snippet, that will allow you to check the amount of common surface area between those two. So if you feel that cells are, touching, maybe a little bit too much, or if cells are touching a lot, then they would have an increased amount of pressure, and that would allow you to implement something like contact inhibited cell growth. So if you wish, you can also count the number of neighbors according to each cell type. So here I've gone through and looked at how many neighbors each cell of type A has, and how many neighbors do cells of type B have. Just as a side note, do let me know if I need to slow down. Just shout out in the chat or by unmuting your microphone, and I won't mind. So to build upon that, you can also measure the opposite type. So just as before, I iterate through all cells of type A, and then I get all the neighbors of those type A cells, and I want to check if the type is type B. And that's how you check if the cells are opposite. At the end of all this, I simply print out that information. So given all this information, I'm going to move on to the first tutorial. So let's get rid of all this stuff. And the goal here is to try to figure out how many of these cells are, or excuse me, figure out how many interactions have happened and prevent those interactions from happening multiple times. So let's say you have two cells that when they come into contact, one of them gives an apoptosis signal to the other. Well, if that signal reaches a certain threshold, let's say like 3000, you set it to a certain integer, that signal is going to accumulate very quickly if you allow that interaction to happen multiple times in the same multi-carbonyl step. So this is a common coding mistake. So I'm going to teach you how to mitigate it. First, you'll create a Python set, which is basically a data structure that does deduplication for you. It's a little bit like a list in that it holds other objects, except every time you insert it, it's going to be idempotent. Let's say your items are 1, 2, 3, 4, 5. You put in another 3. That 3 is going to do nothing, and the set is going to stay the same. So I'm going to set up a basic cell interaction here. simply added the iterate through all cells Python decoration here, and then I iterate through all these cell neighbors. Each time there's an interaction, I want to print the IDs of those two cells. I'm going to open up player here and then open that particular project. So that's cell neighbors. When I run this, it's immediately going to start printing out every interaction between every adjacent cell. And that's what we want to avoid. So this time we instead add in the cell's ID each time we visit it. Oops. We'll also do so for the neighbor. So before that interaction happens, we want to check if we've already seen that interaction or already performed it, and that way it will not happen again on that same Monte Carlo step. So here I've simply written if cell.id is not in the visited set and neighbor.id is not in the visited set, then we're going to perform the interaction. Otherwise, just do nothing. Just start this up again. So this time, for each of our interactions, let's say 133 and 134, it's going to be completely unique. And notice how we do not have another line saying 134 and 133. So we achieved the purpose. Does this make sense? Okay. So I'm going to move on to the next topic. That one was, meant to be kind of quick. So if it didn't make sense immediately, the code is out there on the Google Drive. And I guess also mentioned that some of these topics you don't necessarily need to memorize per se, but it's important that you just see that it exists, and whenever you need to, you can look at the code snippets and pull them down anytime. So the next topic is visualizing bar and line charts. First, you're going to want to open up Player, click the Stop button, which might usually takes a minute. Click Open Demo. And this is a brand new feature under the File menu. It's going to open up this new pane here. And inside that search box, you can type whatever you want. So for example, scientific hist and bar plots. And this is the demo we're going to be working with. So as I mentioned, this is a fairly new feature. So the descriptions are coming soon. Right now, there's just a simple path, which you can copy and paste onto your Windows File Explorer and open it up like that. However, I've included all of these in the module 2.4 folder for convenience. So in the Python preview, you'll get to see there's, well, some code like this. We'll get into it very soon. So the basic premise of creating a histogram plot is inside of the start function, you have to add in a line for creating the plot window. And then after that, you create another new line for each histogram you're going to want to stack. So let's see that in action. So here I have actually 3 histograms. One is in green, a little bit difficult to see. And I have a BOD plot and a foam coarsen in simulation, which allows us to see that there's a whole lot of variation in our cell volumes. So the histogram will tell us there's approximately 80 cells with volume, let's say 25 or so, and 40 cells with volume be 35, 32. So how do we create that plot? A lot of this is based on like similar structure to matplotlib. So if you're familiar with some of those decorations, it's very similar. And inside of the step function, we actually completely refresh the plot at every interval. And to do that, we pass in as our data a list of values that is just numbers. So we create a list of just the cell volume, for example. And no matter what you're trying to create a histogram out of, you're always going to want to have one value in your list for each cell. So I think I'm going to create a simple demo of this. Let's create a new project. So I went into Twit, I clicked CC3D project, and there's a new project menu up there. I'm kind of doing this a little too quickly, so let me show that again. So it's the new project menu. So a lot of this stuff you're able to just keep the same, keep it as default. So just click next, next, next. Under the cell type menu, make sure to have at least 2 cell types to make it a little bit easier. Type A and type B is a mistake. I forgot to delete it. Oh well. We're going to skip chemical fields, and for the plugins, you're going to want contact, volume, surface flex, and I think that's about it. So again, contact, volume, surface flex, and that's it. The goal of these plots is to simply track the cell volume over time, and we're going to need those plugins enabled in order to do that. Click next again, and then finish. So now inside of Twit, you can either edit the stepables.py file, or if you prefer, you switch over to VSCode again, and that's exactly what I'm going to do. So I have the stepables Python file open here, and I'm going to insert a new snippet that's related to adding the histogram plot window, and that's going to create the graphics window part. You want a new graphics window for every plot window you want here, if that makes sense. So this, in VS Code, you can simply autocomplete like this, type something like add histogram plot, and it's labeled start function, and I'll show it again in Twit. So CC3D Python, scientific plots and histograms, and there's one called add histogram plot for start function. So I'll try not to switch too much back and forth between Twitter and VSCode. Maybe it's confusing, maybe it's not, but
Hey, Pete, could you remind us, we have a couple people in the chat asking which plugins you chose in the wizard again?
sure. I'll actually type it out. Surface Flex, Volume Flex, and Contact.
And which snippet did you just grab?
This one is called scientific plots and then add histogram plot.
How is that different than scientific plots histograms, which is right below? Oh, that it is. Okay.
Yep, I'll get there. So the next one goes inside of the step function. So just delete the existing content. But add scientific plot or histogram. The difference here is this one is intended for the step function, and that's going to update the data over time, whereas the other one is just intended for creation. So I need to create some kind of volume list, and that will hold our data. So with a simple Python list, I'm going to iterate through all the cells. So in self.cell list. And create another line for the list itself. Volume list.append and cell.volume. Okay. So after that, make sure to replace the value array with your new list, and you can get rid of the other ones. So we're only going to keep one of these histograms, and the more of these lines that you have for adding new histogram plots, it allows you to stack histograms onto the same window. Up here, you can specify the title, and there's also another option for a number of bins, which should be right here. An example of this is we actually have two plots that are doing the exact same thing. It has the same data in them, but because the blue one has more bins, it appears more precise. Well, not quite the exact same data, but you get the idea. But one important call out here is the plot name must be exactly the same as the plot name that you created with. And this is a similar concept with the line charts, where every time you create a new plot, you have to note down that name. So copy it exactly from the start function into your step function. So I'm going to open this up in Player and make sure that it works. It might not. Here we go. So this feature is great, but it can also slow down your simulations a little bit. So I'd recommend only updating your plots a bit infrequently, and we'll show how to do that now. So I see a lot of points in the chat, so let me check. Can you slow down a bit? Absolutely.
I'll just say Pedro just mentioned maybe we don't try to follow along in our own simulation. We just listen to you and just try to get the concepts of what you're talking about.
Right. And as I mentioned earlier, it's not something where you necessarily need to memorize all of these topics because they're very specific to CompuCell. But anytime you want to go back to these simulations and look up the code, they're there for you. And it's just a good idea to get, a general understanding of what CompuCell has to offer.
And we will have the recording of this video on uploaded and indexed with chapter markers within the next couple of days. So if you do need to reference it later in the workshop, you can easily find what you need from Pete's topics here today.
Okay. So I'm going to pause this simulation or stop it, excuse me. And back in the code, I'm going to implement the point I mentioned earlier, which is we're going to update the plot infrequently because that will help us with performance. So every MCS will do over, general cell interactions, but let's say every 20 MCS, we're going to update the plot. So what I've just typed here is the Python module operator. What it means is it takes the remainder of whatever you're dividing by. So let's say MCS is 100 and you divide by 20. If the remainder is 0, that means that the condition passes. So every 20 steps, we're going to update the plot. So the next topic is moving on to the line charts. And for this one, we're going to copy the same information from the histogram plot, but we're going to change the X scale type and Y scale type, as well as add a grid property. So right now, I just typed X scale type equals linear into the add new plot window function. And I'll do the same for Y scale type equals linear. And finally, I'll add in another property, set grid equals to true. And that's going to be Python Boolean, not in quotes. We'll also need to name that window something else. So here's another point. Whenever you create a new plot window, what you're doing is actually assigning a new variable to the Python class. And what that means is you're keeping track of that object within the program. Whenever you reference self.plot window anywhere else in the code, it's going to look up that same plot window. So we need to make sure that it's different from the histogram. Let's call it histogram window. And that's just an arbitrary name that you can name whatever you want. Plot name, I'll also make this one unique, or excuse me, line chart window. That's my mistake. And from there, we're ready to move on. So inside the step function, it's a very similar structure in that you have to update the MCS, or you have to update the chart every like 20 MCS, for instance. But this time, rather than completely refreshing the histogram, you're actually just going to make a call to add data point. And that's going to update the line chart over time rather than clearing out the whole thing. Just make sure very quickly this is the correct line. Maybe not quite. So for the add data point method, it takes 3 arguments. One of them is the name of the plot. Say I call it line 1. Pass in the MCS, which is an automatically passed in property from CompuCell's Python. And that should start to work. Oh, not quite. Okay, my mistake. I called it add histogram plot. There's my mistake. So in reality, it should be called simply add plot. Keep looking at my answer key now and then. So it's very faint. You can adjust the alpha value on that, make it a little more opaque. And this will just keep going as long as the simulation progresses. So I will show the code a little bit longer here. And just so that we have a moment to copy it down.
It might be worth, Pete, cutting and pasting the key code into the chat.
You zoom lets me.
I don't know if you can do all of it at once, but you can do small blocks and people should be able to cut and paste that. I'm actually not sure. Sometimes Zoom lets you do it, sometimes it doesn't, so we'll see. But it might be worth a try. People will certainly have to redo the indentation, but they should be able to cut and paste from the chat the code statements.
I'm struggling. I'm just over the character limit. Okay, there's the start function. And next up is stop. And that's a direct message to Hayden. My mistake. So before we move on, I just want to show one more thing that you can do with line charts. And one of the purposes of this is to be able to track your own built-in properties of cells, or not built-in, but the custom programmed properties, and see how they change over time. So in this simulation, I pick 5 cells every Monte Carlo step to become infected. And since it's a Boolean property assigned to every cell, that makes it idempotent, meaning you cannot make a cell infected twice, and at some point, all the cells are going to be infected. So in simpler terms, it's going to reach a certain threshold here, where it's just going to cap out at 100%. All the cells will be infected, and it's no longer able to choose new random copies. So looking over at the code for that, we're able to assign a dictionary to every cell. I don't know if this was covered before in the workshop, but there's a property called cell.dict, and you can use any Python object to make it a key. It's whatever you want. So here I simply called it infected in a string quote and set it to the Boolean property false. So that's inside of our start function. So an important note here is it's best practice to initialize all of the properties for your cell dict to the same thing. So all of them are going to be false by default, and I simply iterate through the entire self.cell list to do that. Later on in the step function, I use some Python to pick 5 random cell IDs based on the length of my cell list. And then using the fetch cell by ID function from CompuCell, I pass in that cell ID to get my cell. Once I have my cell, I simply add in the infected property and set it to true. Now, once all that's said and done, I come back to try to update my plot by calculating the total number of infected cells. I started out at 0 and iterate through all of these cells, adding 1 to that counter every time I encounter an infected cell. Finally, the line chart is going to round that to a percentage, and then call the add data point function again, using the plot name, the MCS, and the percent infected. So if you need the extra reference, I've added some notes here in the slides about adding histograms and adding line charts. So if you want to, you can just copy paste this code right into your simulation. So next up, I'll show how to take screenshots and make movies. So in CompuCell, this is a bit of a multi-step process for this. You're first going to want to open a simulation, have it running, which is the important part. You have to click the step icon, then click the camera icon to actually enable the screenshot taking process. You're going to go into the configuration menu and then change whatever settings you want according to how often to update the screen and how often to take an image. So I'm going to show that very briefly, but I also have an extra video here that you can watch anytime you want if you want to go through that process again. So let's click the step icon and click the camera icon here. There's no visual confirmation here, so just have to trust that it works. Click the set of tools at the top, and that'll open up the configuration menu. You're going to the Screenshots and Movies tab, and there's a few points here about how often to save the images and how often to update the graphical interface. So the first option controls how often the screen refreshes, and part of the purpose of this is if you set it very high, for instance, like every 100 Monte Carlo steps, it's going to draw very infrequently. So it'd be less useful for debugging things in real time, but it would be more useful if you have a simulation that needs to execute with very brief Monte Carlo steps. You can have it run for a very long time. There's a little bit of a caveat here, which is you cannot set the value to something less than how often you save a screenshot. So something like this will not work. 50 less than 100. You need to have the screen update at least as often as you take a screenshot. There's also an option to save a movie every time the simulation stops, and we'll get into that a bit later. So once you kick off the simulation with these settings enabled, you should see a certain directory start to fill up with images. In order to get to that directory, though, you can go to the Setup tab, go to CC3 Workspace directory, or the project location. Mine is set to this particular folder. So I'm going to copy this and put it into Windows Explorer. So here you can see I've run a whole lot of simulations And there are some examples I've set aside for this very purpose. So they'll click inside of a simulation that's run recently. And you don't necessarily have to follow this in real time. We'll just, briefly see how it works. One neat feature of the screenshot taker is that it will create a new screenshot for every type of cell field, whether that's, a cell field tracker that we'll get into later in this module, or a chemical field that we'll get into later in the week. So one of these is my chemical gradients, and the other is simply for the cells. So these images are annotated based on the Monte Carlo step that the image was taken in. So I took them every 100 steps, and they're annotated as such. Okay. So now on to making movies. So in order to use our movie making feature, you first must have screenshots taken. Can't make something from nothing, right? So again, you're going to go into the configuration menu. It's the toolkit. Click on the screenshots and movies tab. And click on the create movie now button if you want to do it manually, or use this option to create one every time the simulation ends. So there's one downside of the automatic movie creation though, which is there's not really a good indicator of whether or not the movie is in progress other than monitoring the terminal. It will tell you, created so many movies based on so many screenshots. So it is a good idea to create infrequently with the manual process like this. So once you click that button, you will select the directory of your choosing. And wait a few moments, and it will start to generate movies in that directory. I saw a question in the chat. Is there an advantage to using a separate class to generate or to update your graphs? This is quite a while ago from the histogram module, rather than just checking everything inside of an if statement with MCS. Absolutely. You can do that very easily. I don't really mean to derail the conversation here, but inside of the .py file, you can actually register another steppable and set the frequency to be a bit higher. So back to the movies feature. It just finished our movie creation, and we can check inside of the directory by clicking Show Movie in File Browser. And it now has some .mp4 files. I've done it many times before, but it will generate one based on each cell field that you have. So there are other options here as well to pay attention to. One of them is the frame rate, and that affects how quickly the movie will play. If you have a very low frame rate, the movie won't look great, but it's great for if you want the movie to play slowly, if you only have a few images taken. So for example, if you set it to 1 FPS or 2 FPS, then it's great if you only have 10 images on hand. The quality is simply a measure of the resolution, and writing the MCS on the frame allows you to visualize the MCS in real time. So that's about all there is to say about movies. The next topic is message windows. Message windows are great if you want to publish your model and have other users view data about it in real time. So one use case of this is you want people to see some background knowledge inside of the start function as soon as your simulation boots up. And similarly, you can see in real time some data like, the cell's volume, and maybe print out, like, for example, the average cell volume at each Monte Carlo steps. rather than putting it on a histogram or line chart. So I'm going to close out the simulation again, click the stop button, and open demo again. This is the file open demo button. And the demo is called message window. Click open demo, play, and it's in blue font, so it's going to be very difficult to see. But it's printing out simply the Monte Carlo step that we're on. It's sitting 710, 750. And if you look at the code, we create a message window, much like the same way we did with a histogram, by assigning a new property to the Python class, self.messageWindow. You can call it whatever you want. And there's a built-in method from CompuCell called add new message window. And in the start function, if you want to, for example, set like a really long tutorial description of what the model is and the biological background, it's a great place to do that if you want to publish your model for educational purposes. Then inside of the step function, you simply write print. It's the same call as before, but you can do it whenever you want. We also have a call to clear if you so choose. So I'm going to move on from message windows. It was a very fast topic, but great to see if you are interested in that sort of thing. Next up is the steering panel and sliders. This will allow you to adjust your simulation in real time. This is going to be one of our last topics, so hang in there. The built-in demo this time is called the elongation demo. There's a lot of these, and they're all under the PyCore specs folder. So you can type elongation demo, and it's going to be this one. So this simulation is actually Python only, so that's why our demo browser tells us there's only a certain files available. So when I click run on this guy, there's a new window this time that pops up, which is our steering panel. The steering panel has some sliders here that you can drag to adjust the properties in real time. So all these cells are pretty basic, but once we try to adjust the target length or the lambda length, that will make them acquiesce to those certain dimensions. So let's increase the target length to 20. You wait a few moments, and you won't see much at first. You'll need to increase the lambda length to make that process happen a lot faster. So I'm going to increase it to a little bit more than that. What we should see eventually, though, is the cells start to turn into more of like bacteriophage sort of size because we increased their length. So besides that property, there's also one for lambda chemo, and that stands for lambda chemotaxis. We'll get into this in more detail throughout the week, but here's a little bit of a teaser. You click the drop down in the graphics window. It's a little bit disorienting. It's like way over here, but each of these cells is actually secreting a chemical that's completely arbitrary. We just called it F1. And by increasing the level of lambda chemotaxis to make it really high, and click play again, essentially pause it by adjusting the cell field, those cells are going to start to migrate towards each other and form clumps. I was just checking on the chat real quick. Do call out something in the by unmuting if you have anything urgent. So I posted here some documentation on creating the steering panel. You can look at the code very briefly, but here's something for your reference. So in the module 2.4 code, it's under elongation demo. Click on the steppables file, which, because this is a Python only simulation, it's simply going to be the only Python file there. And what makes a Python only simulation a bit unique is you have to register all of these plugins manually. I wouldn't necessarily recommend it for beginners, but it's something to consider for the long term if you plan on using CompuCell for a long time and want to migrate away from XML. So one might ask the question, why would you want to do that? Well, Python gives you a little bit more control, whereas XML allows you to have a lot more built-in options than a Python file would. So inside of the main stubable, we start out by creating a simple wall around the simulation. This is another built-in method, and it's a little bit hard to see, but you can see a certain border of frozen cells around the simulation. We call the add steering panel method, and I believe this one is actually built in. Inside of it, we'll add in a number of parameters according to target length, lambda length, and lambda taxis, as you saw with these three sliders. And the slider is not the only type of widget you can use with the steering panel. There's also combo boxes. And using these different options, you can adjust the range that allows that you're able, excuse me, you're able to adjust the range that you can adjust to. So there's also another method called process steering panel data. And this method responds to the adjustments that the user makes to those sliders. So for example, whenever someone adjusts the target length slider, it's going to get the value from the steering panel and then pass it directly to the length constraint plugin. The documentation might help you out a little bit more here because this is a Python only simulation and it's summoning the plugins directly. But once you've adjusted those values, you can then simply call the steer method. So if you wanted to do this in a standard simulation, rather than going through all this Python only nonsense, you can simply write in for cell in self.cellList. And for each cell, you want to adjust its target volume or lambda volume, target length in this case. Set it equal to the steering perimeter value and call steer as before. But you might be asking, what are all these other values here, such as T1 and F1? This is basically adjusting the cell type, T1, as well as the name of the chemical field called F1. And for those, we customarily have them in the XML file, but they're up there towards the top. So the very last topic for today is tracking fields. This one is called Module 2.4 Cell Field Base. And this one is going to be the most interactive one of today. So we're going to be starting off with a blank slate, and I'm going to walk through how to create self-tracking fields. So first, let me show what you'll be building. So I have two windows open. In order to create a new one, simply go to the Window button in Player and click New Graphics Window. And that will generate another window like this. Then in the dropdown, you want to select Signal Field. You won't have one immediately if you're in a blank slate simulation. You have to create those chemical gradients yourself. Or the cell fields, excuse me. So what I've done here is actually mapped out how many cells are touching the opposite type of cell. And I only add in a cell signal if it's the yellow type cell. So every MCS, those yellow cells are getting a little bit of signal from the red type cells. And one possible use case of this is, let's say, for example, as I mentioned earlier, the red cells are giving a apoptotic signal, and those yellow cells need to respond to it somehow. But rather than just killing off your cells right away, perhaps you want to, watch your simulation in real time and see those, light up bright red before they start to shrink down into apoptosis. So this is called the cell field base. And let's go to the separables file. So first up, you're going to want to create a signal field, and that would be a global Python variable. This might be a bit of a new concept for some, but the basic idea is that you create a variable outside of your class, and then by using the keyword global before it, that will tell Python what you're talking about. So it'll say, Python, please look up the value according to someplace outside the class. In the signal field, we're going to define it as self.createScalar field according to cell level pi. We do have a snippet for this, which is it's going to be a lot more convenient. You can name it whatever you want. I'm going to call mine a signal field and set it equal to that signal field variable. The reason we're using this global variable is so that it's a lot easier to access the cell field inside of whatever separables we create. So let's say you have a mitosis separable or a necrosis one, then you can still use the signal field variable. And later on inside this step function, we're going to add in our data to it. So first up, we're going to assign a signal property to every cell. Let's go to the all cells plugin. So write in for cell in self.cellList, as always. And for each cell, access its dictionary attribute, signal level, and set it equal to 0. The next step is to choose a random cell that we're going to seed and be the only cell that transmits that signal. So the basic idea I have is, this is somewhat like, almost like an infection spreading between people in real life. One person catches the cold, and everyone else they touch then catches the cold and is able to spread it. Yeah, they're contagious now. So I'm going to add in lines at the top. From random, import uniform and ran range. I'll just copy it right into the chat since it's kind of a pain. There's a question in the chat. When do I use VSCode and when do I use Twit? I'm going to just show that slide again. It really comes down to personal preference. I recommend using Twit for beginners, but VSCode is also great if that's something that's already familiar to you. For some people already come in their maybe programmer background or they're familiar with VSCode from other projects. So having to learn Twit is just one more thing to learn. But Twit allows you to have a few more features specifically related to CompuCell. And the editor is a little bit less sophisticated than what VSCode provides. So after that, I'm going to pick a random index according to how many cells I have, and that will allow me to randomly choose a cell in the simulation that's going to be infected with our signal level. So what this means is we check the length of our cell list. So let's say there are 50 cells in the simulation. Python will choose a number from 0 to 50 and you give it out as random index. Then our initial cell is going to be equal to self.fetch cell by ID, which we're going to assign its dictionary attribute something a little bit higher. So inside of the step function, we have to copy paste the global signal field because, as I mentioned earlier, it's a way for Python to know what you're talking about when you're using the global variable. So anytime you switch context between moving between functions, you need to access that global variable again. We're going to apply one of the concepts from earlier, which is creating a set, let's say, of visited cells, and that will prevent us from processing the same cell twice in one Monte Carlo step. We're going to iterate through all the cells for cell and self.cell list. For each cell, if the signal is greater than 0, we're then going to infect the neighbors. So we're only talking about that one seed cell at the very first Monte Carlo step. Now let's iterate through all the neighbors. So that one's going to be the visit snippet and cell neighbors. And every time you iterate through cell neighbors, there's this built-in line here that checks, does the neighbor exist? And it's important to keep track of that because it's possible to have something called a null cell or a medium cell, and you don't want to process those because those will just be empty space in the simulation. So we're now going to set the signal level of that neighbor cell to something a little bit higher. I'm going to run this in the Python intro module. You simply add 1 to the existing value that we found in the Python dictionary. And because we set it to 0 earlier, that value is stored in memory and ready to use. Now, the important part now is to adjust the signal field that we pulled in from the global variable. This is what's going to allow us to actually visualize that hidden custom attribute that we assigned to each cell. So the cell field is much the same as a Python dictionary too. So the keys are the cells, which in this case is a neighbor cell. And to visualize the value, we set in an integer, which is going to be the signal level that we just set in the line above. So here we set the dictionary, and here we get a value from a different dictionary. So let's see if that works. Hey, we have an error. This one is could not find the neighbor tracker plugin. So this is expected. In order to be able to iterate through all the neighbors of a cell, you need to install the plugin in your XML file. If it's missing and tweeted, there's something called neighbor tracker plugin under the CC3D ML menu. And it will look something like this. So here it is in chat. So now when we change that dropdown, we're starting to see, oh no, all of the cells are having the same signal level. We actually wanted to change only one color of the cells. So in order to do that, we're going to add in another condition to our if statement. So every time we increase the signal, we're first going to make sure that the cell type is the same as the cell that's trying to give off the signal. So we write if neighbor exists and cell.type is equal to neighbor.type. Let me just run it quickly to see if that works. I'll come back to the code in a moment. So window, new graphics window if the other one happens to close. So here we go. It's working out okay. So we'll just leave up this code for a moment and give everyone a time to replicate it themselves. I think this is our last topic for today. Let's see. Yes, it is. So if we want to put out the module questionnaire, we can. And I'll just leave the code open a little longer.
As I said, some of the things Pete covered today, we haven't gotten to yet in detail in the class. And so they'll be more familiar to you when we come back to them. Don't worry if there are some things that you didn't catch. Everything to learn a language, you need to hear things many times. You don't learn vocabulary after hearing it once. So I definitely encourage you to look back at the videos of Pete's, and you might Also, I put in the chat some links to the various manual pages covering some of the topics that Peter addressed. You can use those now. Now that you know the terminology, you can find how to look them up. And also, there are different versions of some of these topics. Some of these things are very new because Pete was the one who wrote the code for them, and so they're brand new. But for some of the top things that have been available in CompuCell for quite a while, there are videos, for example, from last year or from the courses I've taught as regular courses here at Indiana University that might go into a little bit more detail or cover a little bit more background for some of these topics, because we asked Pete to cover a lot of material in a short amount of time, which he did a great job of. But if you want sort of other points of view or additional slides, these kinds of things, I put in the chat some links, and you can certainly search in the YouTube channel. You could search by topic and probably find some additional material as well. So one thing we could do literally would be to walk through the Twit, maybe in the discussion session today. We can actually literally open up the Twit and pull down the menus and see how the code snippets look. And we could also walk through the manuals. It's a big program. It's got a lot of features, and so sometimes it's a little hard to know where to look for things. And so as you're learning,
let's show one of those manuals now.
Thank you, Pete. That would be great.
So when you come to our reference manual page, which I'll put this link in the chat, there's a search documents button here. It's not super sophisticated. It's going to be something more like an exact match, but let's say you type in surface. It'll give you all the documents related to our surface plugin. And we also have some appendix files that kind of list out every single feature out there in CompuCell. And some of these plugins are going to be a bit more beginner-oriented. Some of them are going to be more reference-oriented. But I hope they'll be of use to you.
Pete, could you open that Python tutorial section, because that might be useful for beginners?
So here it tells you how to create your first project, add in a new separable, and what are these things? Tells you how to create a mitosis separable. This one's one of my favorites. It actually just puts in a whole Python file there for you, so you can copy it and run it yourself. It tells you some of the details that go into this mitosis. So, for example, you have to increase your volume in order to make the cells divide, for instance. So some of these like very CompuCell specific things are all there listed.
And there were earlier today, and Pete would be the good person to go to on some of these things. There were some people who were more advanced who were interested in C++ extensions to CompuCell or coupling CompuCell plugins and forces to external code. And there also are some, both in Twit, there's some support for C++ code snippets, and also there's some developers documentation online as well. And so Pete is a lead developer for CompuCell, and he might be able to give some advice on those issues as well when he has the chance. So there are a number of possibilities. Again, in this class, we have people who have many different levels of experience, and we try to make it interesting to everybody. And so it's okay if you don't follow every lecture. It's okay if some of the lectures are a little too elementary. We hope that overall things balance out, and that people learn at the level that's appropriate for you. Everyone comes in with a different background, and so We really appreciate the different points of view. It's one of the reasons that we like having different lecturers. Gilberto's approach to teaching and Pedro's approach to teaching, my approach to teaching, and Pete's will all be somewhat different. And we hope that each of us resonates with at least a few of you in the class. I really appreciate Pete coming from Salesforce, taking the time to teach for us today. It's really been, I learned a lot from seeing this lecture, and I appreciate that very much. And so we have time
Sure.
for some questions if people have any. Feel free to unmute and ask any questions you like at this point.
And I'd like to say thank you again. It's a lot to bear with me because, I'll be honest, I was only told a few days ago that I would be able to present this topic. So a lot of it was prepared in a hurry, not too much time for rehearsal. So if you didn't follow along perfectly, then it wasn't the most rehearsed. Yes. And I also found out that talking to a Zoom presentation is very much different from real life. It feels like I'm talking to a wall during the presentation. So sometimes it might sound a little bit strange. Thank you for bearing with me.
Okay, are there any questions for Pete? As I say, he covered a lot of material. We talked about sliders, tracking fields we haven't really gotten to because we haven't really, that'll be covered. Fields and their concepts are really going to be introduced tomorrow. But you'll be really prepared for those now that you've seen Pete's lecture on that. The choice of IDE, we typically teach with Twidit because it seems to be easier for beginners, but VSCode certainly has a lot of features that we don't have in Twidit. And so advanced users often prefer that or a PyCharm as environments. So again, you'll see that this is a world with many points of view, and it's really interesting. Thank you, Pete, also for stepping in at the last minute for doing this. I appreciate very much the time you took to prepare that lecture.
Sure. So for the end of the module here, we do have a little bit more time left for Jim Sluka's hackathon and mine as well.
Great. Why don't we go ahead and do that? We'd love to have those presentations.
Yeah, if you are interested, I'll have Jim go first. I'll give everyone a bit of a break from my voice.
Jim, are you there? Do you want to do your
Yep,
extra presentations?
Let me share my screen.
It's completely put you on the spot.
Okay, I'm going to go through this pretty quickly. The idea of this is not to teach you how to do stuff. Instead, it's just to give you an idea of the kinds of things that you can do and kinds of ways of thinking of problems and bits and pieces of tools that you might need down the road that you can always go and find without having to actually understand how to code it from scratch, since you may never use it. So we're in a different place now. We're down at the bottom of day 2. I didn't update the slot. On the CompuCell website, over on the left menu, there's visual examples, and I haven't been consistent in names. Sometimes I call them visual examples, sometimes I call them quick models. But most of these things I'm going to show are linked on this page here. A little screenshot, a little description, and then a link to the CompuCell project if you want to download it and try it yourself. I'm going to go through a couple of these really quick, like I say. So the first one is, what if you wanted to track the location of a cell? So this is a simulation of 4 cells. This is pretty late in the simulation. These 4 cells have been drifting about in the simulation. Here's a track of where each cell has been. This is done as an XY plot, a graph like you just saw Pete and others showing. Every so many MCS, it just puts another dot on the screen wherever there's a center of a cell. This one on the right is a little bit different. This is a user-controlled field, and the field is set to not diffuse. The nice thing about the user-controlled field is you can color the dots by the MCS step. So the blue are the original positioning, and it's drifting through, and the red is the most recent position of the particular cells. So you can track cells. If you want to do more complex tracking, you could always export the center of mass of every so many MCS for each cell and do some other analysis in it. But this is kind of a quick and easy visual way of doing it. You can build fibers in CompuCell. This question we get a lot. Here's a 2D fiber model. Here's a 3D fiber model. It's easy enough to create cells in CompuCell that are just straight lines. The challenge here is if you treat these fibers as cells in a 2D model, a regular cell can't cross over one of these lines very easily. So a different approach to treat the fiber in a 2D model is to treat the fiber as a non-diffusing field. So you'd create these green lines in a field. You could then have your cells chemotax along the fibers. In 3D, it's not as much of a problem because the cells can move around a fiber because it's got 3 dimensions. So you could also do fibers in 3D if you wanted to. Anytime you have to create a more complex layout of cells, something that goes beyond blob or slab initializer, you can create cells inside of your steppable. Any logical way that you want to write the mathematics to create locations of cells, you can set them up any way you want. This little demo makes nice round cells. It's got a function that returns all the pixels in a round region, given an offset and a radius. And this example just goes through and creates a circle of cells of these 3 different cell types. And that'll give you an idea of, if you can figure out the Python code to get location, this will show you how to actually create cells, put the pixels in the cells, and do the other things you need to do to make a cell layout. This cell layout in general can get very complicated, so it's nice to have the kind of the basics under your belt. You can import images into CompuCell. This is my daughter's dog. You can read it in and make a user-defined field in CompuCell. So now this is a field that you can query, do whatever manipulation you want on it. CompuCell only has this red-green color bar, so you can't get the colors right. But it does retain all the pixel information, the RGB information for each pixel. A little more complicated, it is possible to draw a complex cell layout, and then import it into CompuCell. We used to have a tool called Cell Draw, I think is what it was. There was this basic idea, but it hasn't been supported in a long time. So if you have a very complex layout, you can draw in Paint or PowerPoint or your GIMP or whatever your favorite drawing program is. Import the image into CompuCell. So this is actually the imported image. Again, we don't have control of the color bars, so the colors are different. But then this example project shows you how to step through every pixel in the image and convert this non-diffusing field, basically, into individual cells of given types. So we have green cells and blue cells, and the white is empty space that's not used. This is supposed to be a vascular tree, a little part of a vascular tree. So you can import cells, and you can create and do analysis in CompuCell. Maybe not the best way to do it if you have complicated, say, histology slides, but it certainly could be done. Another thing, CompuCell, the POTS model lives in a very viscous world. So if you push on something, it moves, but if you stop pushing, it stops. In the real world, if you push on something in the absence of drag, it keeps moving. It is possible to simulate acceleration in CompuCell. So here's just a dropping cell that accelerates as the simulation progresses. And this is done by increasing the force instead of using a constant force. So you can simulate falling. Oh, wrong window. Oh, too fast. This is the same simulation. Now my little red cell has fallen all the way to the bottom. This is a plot of velocity versus time. Here's 0, and these are negative numbers because it's falling downwards. So over time, the cell is accelerating. Its velocity is continually increasing in the negative direction. So this could be tuned to represent gravity if you want. If you use a constant force on the cell, this line plateaus. Once it gets moving, it maintains a constant velocity instead of accelerating. So there are ways of getting around the very viscous nature if you need falling. Often you have multiple windows. You've seen how to you've seen that CarpCell will save animations. Sometimes you want to put the animations together. So we have a little demo. It actually doesn't use the built-in feature. Oops. It doesn't use the built-in animation tool because that's relatively new. But this demo walks you through creating the screenshots for these four windows, filing those screenshots into 4 individual animations, and then stacking all those animations into one giant animation. So this is our bacterium being chased by a macrophage. Here I'm showing cell tracking for the macrophage as it chases it, and then this is the attracted field that the bacterium is generating, and this is the repellent field that the macrophage is generating. So the 2 cells are running away from each other based on, well, one's chasing and one's running away. So it is possible to build up more complicated animations. And so there we have a little demo and some code that would help you get started on making these more complicated animations. This is a simple Durataxis model. Durataxis is change in cell migration based on stiffness of the matrix. And in this model, basically what we start with is a slab with this red marking on it. And the cell's motility depends on what part of the slab they're touching. So if they're touching red, their motility goes down, which would be equivalent to a stiffer matrix. And if they're sitting on blue, they migrate faster. And at the end of the simulation, cells tend to aggregate over the center where the red stiff bar is. And here's a cell track of how everybody wandered to find it. This one is Gilberto's, which I'm not sure if he's going to show. Does anybody know? Has he shown this one yet? This is flow through a restricted pipe. So what we do is we're creating cells here, and as they get created, they push the other cells down the pipe. There's 2 obstacles. There's this gap and then a ball at the end. We have a couple of this one down here at the bottom right. This shows all the cells. I have the cell borders turned off. I'm not going to go into why the cell borders are turned off. There's a lot of cells down here. This is the velocity of each cell instantaneously. All the arrows are the same size. The color coding is the velocity. This is the pressure in each cell. And this is the pressure per pixel, which is actually what you would want if you're doing a fluid dynamics model. So here's the animations. Here's cells moving. You'll see them hit the barrier. See the acceleration goes up, the red arrows, and drops on the other side. Velocity goes up, the red area. Here's cell pressures. You get high pressure for cells, constriction, and we'll also get down here as well. And then
Sorry,
this is
your audio went out there, so you're going to have to explain this one again.
Should I start this one?
Yeah.
So those are velocities, and red means fast and blue is slow. And that's so it's accelerating as they go through the constriction. This is the individual cell pressures. See the pressures go up at the constriction and drop. A more fluid dynamic is to actually calculate the average pressure at a pixel, whereas this is pressure in cells. This is the pressure of the location. So this is an animation of the pressure changes. You see the pressure goes up for the constriction. You get a nice pressure drop through the constriction. A very low pressure on the other side of the constriction. And then the pressure goes up again as you start to hit the red or the round barrier at the end. So CarpCell is really not meant to do fluid dynamics, but there may be cases where it would be useful to get it. It will at least get the general characteristics of the fluid dynamics correct. This is another one of Dr. Thomas's simulations. I don't know if he's going to show this. This is lamellipodia migration. So some cells migrate by having a leading edge that's stiffened by actin fibers, and that leading edge migrates and it drags along the rest of the cell. So one of our cells here is the lamellipodia, a cytosol and a nucleus. And this simulation just shows that kind of a cell crawling around and dividing. So it divided. They're told to migrate in a straight line for a while and then change directions. this particular model has periodic boundaries turned on, so the cells wrap around if they go off an edge. And there is a bug because this cell divided and lost its nucleus. So this would be easy to turn into an animation where, for instance, you put a nutrient field, a stationary nutrient field down, and let these cells migrate up the nutrient field. At the same time, have them destroy the nutrient field, and then have them starve to death when they run out of nutrient field, when the large number of dividing cells eventually has wiped them all out. Watch that guy again. They shouldn't have synchronized that. That was just random chance they synchronized like that. So that's the last of them. So those are all, well, most of them, so the last two are linked from the visual examples. And so there's some description, sometimes a Word document, and always a zip file of the CompuCell project if you want to see how it was done. All right, so that's all I have for that one.
Great presentation, a lot of material in a short amount of time, and certainly there's a lot of cool features built in the CompuCell.
Great, thank you.
Uh,
Questions before Jim, or do you want to have Pete? Do you want to present and then have questions for both of you together?
We can do questions.
I'm
right
sorry,
now.
I lost my audio. I think I'm back now. Could you, if you had a question?
Maybe we'll hold off on the questions.
Okay.
Yeah, your audio is breaking up again, Jim. As soon as you said, I think I'm back.
Great. This is a hackathon project that I did last year in the workshop, and part of it is replicating an existing model, but incorporating my own hypotheses into it. We really strongly advocate for you to replicate existing models if you're not sure what to create, because you'll always learn something by doing it. And any person would create their model just a little bit differently than the last person. So you'll, might uncover something new. So this is a model of germinal centers, which is a certain fraction of the lymph nodes inside of your body. And it's where your body develops its immune system superweapons. Essentially, B cells migrate between two zones of a germinal center, the dark zone on the left and the light zone on the right. The dark zone is where the cells are allowed to proliferate, and they do several rounds of recycling in order to develop the perfect antibody to match a foreign antigen. So there are two types of the B cells. The first differentiation is called central blast, which is the proliferating kind. It's going to divide 2 to 6 times on average, and through each of those cycles, it's going to undergo what's called asymmetric division, meaning it'll lose some of the antigen between those two daughter cells. And some of the antigen or one of the cells might get a lot of the antigen, and another one might get only 12%, for instance. And once it reaches the division limit by running out of antigen, it's going to become a central site and start migrating towards the dark zone. The central site is the quiescent version, and it's going to wait for signals from T follicular helper cells, otherwise known as TFH cells, in order to know whether or not it should undergo apoptosis or migrate back to the light or the dark zone to start proliferating again. So this is our selection process. It's a way for the T cells to kind of grade or judge how good our B cells are going to be at mitigating the threat. If the antibody is highly effective, they're going to differentiate into plasmablasts, which then are like the weapon cells. During this process, you also have another player over here called the follicular dendritic cell, or FDC. These guys have really long arms, and they stretch over to the B cells to replenish the antigen, allowing them to then develop their DNA more effectively in the dark zone. The proliferation process is called somatic hypermutation, and what that means is the B cells actually mutate their DNA so that they can develop a different kind of antibody and express it on their surface. I won't get into too much more detail about the actual proteins on the surface. There's like, some T cell receptors and B cell receptors, MHC class 2. You don't need to know it, but what's more important is that these receptors allow the B cells to migrate back and forth between the two halves of the simulation. Now note that these receptors are kind of like a fictitious concept in our model. We'll get into it a little bit later, but by assigning a certain property to our cell or changing its cell type in real time within the code, that controls which direction it will migrate in. So a lot of the parameters are kind of just scaled down from the literature. That's allowed me to test and debug my simulation more effectively within that 2-day hackathon period. So there's about half of the number of centroblasts, for instance, and there's one more cell type I forgot to mention, which is stromal cells. Those guys sit in the background of the dark zone, and I like to think of them as the background cells because they have principally no function and are just there to secrete a CXCL12 gradient that makes the cells migrate when they're ready to proliferate again. So part of the hypothesis I formed is that the number of antigen that a B cell retains when it undergoes division affects how well or how many generations it's going to have in the dark zone. And in addition, how many antigen the B cell picks up when it visits the follicular dendritic cell, the one with the long branching arms, is going to increase its survival chance. Because let's say, for example, a B cell picks up a really large number of antigen by the FDC, then that will allow it to divide, the maximum number, 6 times back when it returns to the dark zone. That will make it have more effective DNA, theoretically. So that DNA is going to be more effective at creating the perfect antibody. And when it comes back to the T cells to be graded again, the T cell is going to judge it appropriately and give it a survival signal. So I incorporated this hypothesis into my algorithm that I call affinity-dependent antigen collection. Essentially, a follicular dendritic cell only gives out a limited number of antigen at a time, and the level of antigen it gives out depends on how long it's in contact with that B cell. It's going to scale based on its affinity score. Affinity score is basically just like a matching between how well the antibody is at combating the foreign antigen. In my simulation, we record the antibody as just a simple Python list, like ones and zeros. But in reality, it's going to be, actual proteins. It's going to be a bit more complicated. So here's a fun example of a case where simplifying something down in a model is not just done by me, but the exact same things in the literature, and it happens to be quite close, despite being so much simpler. So in addition to the FDC phase, we're going to have the B cell bump into a T cell, and on contact, the B cell is going to be under the pressure of a timer. If it gets a lot of points from the T cell, or survival signal that is, then it's going to be allowed to survive, and the level of survival signal that it receives is proportional to its current affinity score. If the B cell is in contact with the T cell for a long time, but doesn't receive much survival signal, then it's going to need to undergo apoptosis, and the body is a little bit ruthless. So, as I mentioned earlier, the antibody is expressed as a simple Python list. So within the code, we simply check like, is this an exact match, which is what the Hamming distance means? And how many of those lists between the antibody and antigen are different? If they are, we add 1 to the Hamming score. And then we scale it up using an exponential. So one thing I found out from running the simulation is I could actually eliminate these stromal cells, which secrete this background chemical, because they take up some extra space, some extra processing power, and don't really provide that much to the simulation. They don't have too much significance beyond that. And a lot of times this is something you'll need to do. Just cut down your simulation, make it as simple as possible to replicate the scientific problem. So here you're also seeing 2 features at work. Here is a chemical gradient that measures, like, on the right side, we have this high concentration of one of my chemical gradients, and on the opposite side is another chemical gradient. And based on what cell type our B cell is in CombiCell, then it knows to chemotax one way or another. So previously, it was this like very particular pattern based on how much the stromal cells secreted that chemical. But CombiCell also has a simple linear gradient that operates much faster on your GPU. So here's a simple video of my simulation in action. So as soon as it kicks off, you start to see some of these B cells multiply. They're going to have very dense numbers over here. And once they've undergone a certain number of divisions, start to migrate right into the light zone. These giant blue cells are my phylogenetic cells. Notice how they don't have the long arms, but instead I just make them bigger. They're easy to bump into. It's another way to simplify your model. And at the same time, they're going to bump into the TFH cells. I kind of set the contact energy so that they would all just kind of cluster into each other at once. In reality, the cells have to travel like from one cell to another, and it's a bit different. So as the simulation progresses, you'll start to see the average number of affinity go up. And that's measured by the green histogram and the yellow line chart. And you also see the plasmablast generation upon exit time. What that means is a fully mature B cell is called a plasmablast, and when it's ready to exit, then it weaves through the light zone, or excuse me, weaves through the dark zone. My mistake. So as you'd expect, the overall generation is going to be quite high. 7th generation B cells are going to be more successful, but you also see some stragglers towards the end become mature as well. And this is precisely why you might want to use line charts. They'll reveal to you insights that you wouldn't be able to gauge just by looking at a mess of cells. Here's a very quick use case of the cell field that I showed earlier. You're going to assign these custom properties to your cells, which in my case is affinity, and then measure, based on like how bright those colors are, how good is the affinity. And I just showed a bit earlier the same thing, how the histogram might change over time. And I've shown these a bit larger here. But in general, I was able to pull the parameters from the literature. Some of these are very similar, and I'd recommend defining, like, as you're starting out or before you begin programming, what is MCS going to be equal to? Because our Monte Carlo step is really just like a fictitious concept used for modeling. In reality, you should set it to something like, let's say, 1 Monte Carlo step is equivalent to 1/10 of an hour, for instance. And then, by writing that note down to yourself, you'll then have a standard for yourself for all of your parameters in your model. Some parameters may not be precisely translatable into your model, and that's okay. It comes down to, makes things interesting to develop things yourself and see if you can replicate the results. So I think that's about it. I talked about asymmetric division, and my source code is available on GitHub if anyone would like to take a look. It gives you kind of a general idea of all the features in CombiCell.
Thank you, Peter. Any questions for Peter or Jim, if Jim didn't lose his internet connection before we break? I want to bring something up. We probably need to say it again, which Peter just alluded to, which is time scale. We have this funny term, Monte Carlo step. And this question always comes up, which is, how does Monte Carlo step relate to real time? And in certain ways, there is not a problem with that, but the algorithm we use to move cells moves them by creating and destroying pixels in the cell. And effectively, one Monte Carlo step means trying to update every voxel in the lattice. In fact, it's stochastic, so not every voxel actually gets updated every Monte Carlo step. So the most that a cell could move in one Monte Carlo step is one voxel. In fact, because of the stochasticity, you can't move a whole voxel per Monte Carlo step. The most you can move is about a fifth of a voxel per Monte Carlo step reliably. And you'll see that if you take a cell and you apply a force to it, as you apply the force, as you increase the force, the velocity of the cell will increase linearly up to a certain point, and then it'll saturate. If you keep pushing harder, it goes at the same speed. And that speed limit of about 1/5 of a voxel per Monte Carlo step sets a limit on how your timescales work. In your simulation, you know what the length scales are because you have a cell. If you represent the cell as 5 pixels across, and the cell has a size of 10 microns, then you've defined one lattice site as 2 microns. And then the fastest you can move is about 0.4 microns per Monte Carlo step. And so now you can ask, in reality, how fast do your cells move in the real world? And once you know what the fastest your cells move is, then you have to set the time scale of Monte Carlo steps to be something that is smaller than that time interval. You can make the Monte Carlo step represent, suppose that represents a minute, is the fastest you can make things move. You could make a Monte Carlo step represent 30 seconds or 10 seconds or 5 seconds. You can make it you can make it finer grained. But if you make the Monte Carlo step too big, the cells aren't able to move fast enough to represent reality. And so that's the fundamental limit when you're picking the assignment between Monte Carlo steps and real time. Sometimes we cheat. Sometimes we accept that the cells don't actually move in the simulation quite as fast as they do in the real world. In particular, if the cells really move very fast, for example, some immune cells move very quickly. And in that case, you have to use quite a small, one Monte Carlo step might represent a second or 2 seconds or 3 seconds. And then your simulations become fairly slow. In the simulation that Jim Sluka showed of the liver sinusoid, where you're doing explicit blood flow, blood flows very, very quickly in capillaries. And so you have to then make the Monte Carlo step to be very small, to make it 1/100th of a second or 1,000th of a second. And that makes those simulations very long because you have to run a lot of Monte Carlo steps. And so there's always a trade-off. You have a lot of flexibility in deciding what your time scale is. Just the way with an experiment, when you're taking an image, you might take an image every minute or every 5 minutes or every 10 minutes. But if the image takes 5 minutes to take, you can't take an image every 1 minute. There's a limitation, an experimental limitation on how fast you can take images. Similarly here, you can make the Monte Carlo step represent a smaller amount of time, but there's a maximum time set by the fastest moving cell in your simulation. Does that, and we can come back to that, but it came up here, and I think it's something that we probably you need to digest it a little bit. When we go to explicit forces, you'll see it in action.
It seems the same would be true for space as well. So for time, yes, and for space, I'm thinking of an overlay of a lymph node, where the germinal center could be circled, and you could see the actual space and the movement and the migration. You'd probably need to have that correct spatial dimension to run the simulation correctly.
That's right. I mean, typically you can't simulate enormous areas of tissue. In other words, if you're going to try to simulate every cell in a cubic centimeter, you can't do it because there are too many cells. So in reality, you can typically simulate in a reasonable amount of time a cubic millimeter of cells if you're doing in 3D, or perhaps a few millimeters by a few millimeters in 2D is reasonable. But you have, again, some choice of granularity. If you pick a 1/10 of a micron per voxel, you'll have a lot of spatial detail for your individual cells, but you can't represent that many cells. If you pick 20 microns per voxel, the problem is that one cell fits inside of a voxel, and so then you're not able to use the method. So yes, the size of the voxel has to be smaller than the smallest thing you're trying to represent. So yes, there's a granularity also in space. Absolutely. Typically, since we're
single cell is
representing
roughly like 1 by 1 micron, yeah, a single cell.
no, well, maybe if you're doing bacteria, typical eukaryotic cells are between 5 and 25 microns. So we typically will use a lattice size of 1 micron, 2 microns, 3 microns, 4 microns. But yes, if you want to represent bacteria, which could be a 1/2 micron by 1 micron, then you'd have to use a smaller lattice scale. Great point. Any other comments? Again, I didn't want to cut off discussion with Jim and Pete, but since the conversion time issue came up and we hadn't really talked about it, I thought I'd say a few words. Yes, representing individual virions is a pain. You probably don't want to do that in Congress. You can, but you can also often with something like that get away with making them bigger than they really are. Just the way sometimes you can have cells teleport, or you have more cells which move slower, which have the same effective behaviors. There are tricks that you can use to speed up the simulations, but you have to think carefully about what kind of approximations you're making when you do that.
I have a question. So I was a little confused when Jim mentioned the image of the dog. So what was going on there? Like, are we trying to kind of like process the image and differentiate the object? Like, what was going on there? I missed that part, sorry.
You mean on importing an image into CompuCell?
Yeah.
Well, one would be to import a histology slide and use that as your initial configuration and try to segment the histology slide. So, a tissue section slide. Another would be if you have some drawing of some complex initial layout, and it's easier to generate a drawing than it is to try to create that cell layout in Python in CompuCell. So you could make a drawing of your layout and then import that into CompuCell as an image, and then analyze that image to generate your cell layouts.
Okay. And how well can it kind of like distinguish the outline? Like suppose I give it a cell, an image of a cell. How well kind of like with many of the tracking algorithms, like one of the primary obstacle is kind of like determining the cell layer, the outer layer of the cell. So how well can CompuCell deal with that?
So it can't.
Oh.
No, I wouldn't say that. You can, because you can change what you tell that segmenter to do and say, instead of outlining the cell, you tell it to draw a solid circle. And that would be
Another-
fairly easy to import into CompuCell.
Another thing that you can do, which actually works very well in CompuCell, is very often you don't really care about the exact shape of the cell.
Yeah.
You do care about
Yeah.
the cells being roughly in the right position. And
Yeah.
so if you know the nuclear positions, because you say have a histone GFP label, and so you know the identity of every cell in the system, and you know the nuclear positions, and you know their approximate volume, you can set a cell to start out, nucleate a tiny cell at each nuclear center, and then set its target volume to be approximately the correct target volume. And then those cells will grow up and they'll push on each other and they'll create a tissue that will have compact tissue of cells. The exact boundaries will not be exactly where they were in the biology, but you'll have the right size of cells and you'll have the right number of cells and the centers will be in the right place. And that's actually usually pretty close to the real cells. And so that's actually a really nice way to create an initial condition, much nicer than drawing squares to begin with. Something that would be nice to have in CompuCell, which doesn't really exist, is instead of having start and step functions, there should be start, initialize, and step.
Yes.
So that you can run some number of time steps in an initialization mode and then use that. You can do it by hand, where you say at time Monte Carlo step 1,000, change what you do. But that's not a built-in thing at the moment. You can also run the simulation as an initializer and then save it and then read it back in as an initial condition.
I see. Okay.
So there are a lot of different ways you can do that. So again, depending on what you're trying to do. One of the reasons a lot of these things aren't implemented in CompuCell as hard-coded things is because everyone wants to do it slightly differently. And if you define a predefined function to do it, then it'll do it in those ways. And people will always say, well, that's almost what I want. Please add this additional feature to it. And then you basically reinvent Python. So, but it's a good point. We don't really talk about file handling. Maybe Jim will show you a little bit how to read and write files later on in the week. We have something called Fyffe, which is a very naive, basically voxel-based image format, which CompuCell can read. But you can certainly read an image and then scan through the image in CompuCell and then create cells at the voxels positions and have them grow. We actually published a paper on that many, many years ago because we actually used an early version of CompuCell to do image segmentation. With exactly that method. You start at the centers. We could identify the centers of the cells, and you grew them out and let them push on each other. And it's essentially a Voronoi construction in that case.
Okay.
It's a pretty easy way to do it. Other questions? Again, I didn't mean to take away from the questions for Jim and Pete, but that one is, I think, a particularly interesting one. Ramon, you had a question.
Right. Sorry to interrupt.
Yeah.
We'll also take questions on Slack if anyone has to hurry out right away. But go ahead.
Yeah, thank you. Yeah, I just wanted to mention on these imaging things is that we develop a small snippet in Python and C++ that reads the DICOM images, TIFF images, and also NII images, and do the segmentation, depending on the user specification, do the clustering of pixels, for example, even in bezel geometries, and creates a Fyffe file where each voxel is associated with a with a cell ID and a cell type, and it will be available in GitHub like in the next few weeks. So if you think that it will be useful, I can share it also with you, the developers, and maybe have a link in the webpage or something similar.
That would be fabulous. Once you've published it and gotten credit for it, if you want to include it in the CompuCell code base, we'd love to.
Yeah, it seems like segmentation is a huge issue. I know I work for NanoString and we have a spatial single cell profiler where we, against our competitors, segmentation is a huge thing. And we haven't really talked about it too much as a group here about unique geometries by cell type. And what the segmentation different ways of segmenting are. But I think we're trying to keep it somewhat simplified, yeah.
Well, I think, I mean, if you're representing NanoString, I think the idea of taking, spatial omics information and using it to create simulations is tremendously powerful. Because, of course, when you're doing spatial omics, you've killed your sample. By definition, you've got a dead sample. And so to be able to then build a simulation that tells you what might have happened if it stayed alive is really exciting. That's been a dream of ours for many, many years. And we'd love to see that happen. So maybe either this is the kind of thing where, again, if we were in person, we'd talk about it at dinner or in breaks. But I'd love to talk to you more about your interests and thinking about how to put that together. It would be very exciting.
Well, I'm really at the beginning stages. Like, I think about the spatial representation of the different types of B cells and T cells within and outside the germinal center. Transcriptomically or proteomically, we can define those in a much better way than you could with FACS sorting with single cell profiling. But then how do you combine that kind of information with the simulation that Pete just did?
One question you might want to ask yourself is, how much do the initial conditions affect the end result of the simulation? There are whole computer vision projects out there that identify like the vertices in a cell site and like figure out where the cell boundaries are. Of course, then you'd have to translate it over into a voxel model, but it does show that there's a whole lot of effort that you can invest into it, and it might be worth wondering like, how much time do I really want to put into just the initialization?
Right. Well, if you can actually infer the interactome and you have some knowledge about the gene regulatory and signaling networks that are active in the cells, then you can do a lot. And we tend to teach in the class, we focus on teaching reaction kinetic models, but you can also run Boolean network models that are easier to do inference of. Now, we're not the experts in that. In other words, other people are the ones who who think about how to go from the kind of data you collect to those network models. But once you have those network models, you can put them inside of every cell, as Jim showed for the liver, and run them inside of every cell to control the cells. And then you can really begin to ask serious questions about how the spatial interactions lead to phenotypes and to physiology at the tissue level. So I think these things are possible. We're not there yet because we're not a nanostring. So our size of our projects is pretty small. But in principle, I think with the right effort, it would be very reasonable to build a simulation which took spatial omics images and created essentially quasi-living simulations of what was happening.
Herbert
certainly,
Sora last week was saying that there was an issue with incorporating big data based on the way that you would splice the information. And I don't know. But he was saying you typically don't blend omics data with dynamic modeling.
well, reaction kinetic models are relatively computationally expensive, and they require a lot of parameters that are hard to identify. But Boolean network models run much faster, and so you can build larger networks of Boolean models. The outputs are more limited, But we showed that example of the cell cycle and I flashed an example of cell cycle and delta notch as a Boolean network model, and showed that you can control cells that way. And Pedro, in his interferon example that he showed yesterday, had a Boolean network model of the gene regulatory and signaling networks inside the cells. You're not going to be able to run probably 20,000 genes all together at once, unless you have a lot of computing power. You may not need it, but you could definitely run networks with hundreds of nodes inside of each cell and validate those against statistical against the experimental data sets.
The challenge with most of the old omics data is that it's, they take 10 to the 6 cells and lyse it. Or you do, so you get an average, or you do single cell omics, but it's not spatial. So you know what the relative proportions of cells are, but you don't know their spatial layout. It'll be interesting to see how far people can get when they start doing the spatial single cell omics.
Right.
When
Well,
you can start to say this,
Jim,
this particular
she's from a company
cell.
doing that. She's from a company that's doing.
I
So
know.
that's
I know. So
that's exciting.
So we were talking about that in the viral group the other day about doing it the other way around, that if we build a model with a subcellular signaling network that, for instance, upregulates actin, can we create an image that looks like a histology section where actin is labeled? And so we create our CompuCell cells, and then based on the submodel in each cell, find out how much actin that cell has, and stipple that cell with actin molecules. But to try to recreate the detailed histology slide. And I think we could probably try to do the same thing with single cell spatial omics data. So I think what Herbert was referring to is, for 30 years, we've been collecting homogenates and doing sequencing on it, and you lose all your spatial information.
At single cell resolution, the limitation this last year has been about 1,000 plex, and it can be sub down by function from there. Plex is increasing, but it sounds like there's a lot that could be gleaned with subsets of functional gene sets.
Yeah, you don't need to do everything. Although I was in Germany a few months ago. That's when I hurt my back. If you see me wincing, it's because I have a bad back at the moment. But there was a group in the Netherlands that was doing ultra high resolution nanomass spectrometry. And they were able to get a voxel size of less than 1/10 of a micron and do 25,000 species per voxel. And so they could actually map where the actin was, where the nucleus was, where the mitochondria were inside a single cell, in over tens of millimeters by tens of millimeter samples. Their problem was that one image generated 6 terabytes of data, one slice. And so the problem was throughput and saving the image data. But certainly, I'm sure that your company is also probably as or more sophisticated than that, or at least maybe not in the commercially released ones, but I'm sure those things are in development for you. And so seeing that kind of resolution, when you have that level of subcellular resolution, you can say, where is the secretory apparatus? What is the cell cycle? Then my statement that you can't tell what the cell is doing just from the chemicals fails. If you treat the cell as a stirred reactor, where you only know the total chemical composition of the cell, there are a lot of details you miss. When you begin to actually get to subcell resolution, then you really can do a lot in terms of saying, gee, this cell is crawling actively. This cell is in mitosis. This cell is in pyroptosis, all of these things. So yes, let's talk about that. I don't know how much, again, this is a relatively introductory course, but the issues you're raising are very important ones. And I hope we could get to the point where we could have a good, intelligent conversation about these issues. Other questions or comments? We've already overrun we've not only overrun our regular time slot, we've overrun our discussion time slot, but it's wonderful that people want to talk. I want to say how much I appreciate the level of engagement in the chat and people speaking out loud. And also the fact that people are helping each other in the chat. That's really been nice to see how people have worked together to solve problems during the lectures. Any other questions? Hayden, do you have any announcements before we break for today?
No, nothing on my end. Just like I said, keep an eye out as usual for the evening announcements a little bit later tonight. We'll have some links to various things in there for the resources we discussed today.
I just wanted to mention that I just tried to access the documents and the forms for the proposed hackathon ideas, and I couldn't access. I don't know if it's my problem or
The
it's
teaming
actually a
document
problem.
or
The ones that you sent by email. Yeah, the time, none of them, not the survey or the document.
let me make sure
Maybe
they're
it's
still.
a problem on my side.
Let me make sure they're still there. This is one of the dangers of having a folder that a lot of people can edit. Yes, they are. So let me.
Probably not a bad idea to make a non-editable copy of it twice a day to make sure that we don't lose anything important.
Yeah.
Can you please share the links in the chat, because the link I have isn't working.
So there's a link to the theming document, which should have links to everything else, including the folder. Did that work for you this time?
Yeah, it worked. Thank you.
I might have had a typo in the link this morning. And then you should be able to follow these links to get to the rest of the hackathon information. But again, it should be all accessible through the student materials folder as well. There's a separate hackathon folder in the student materials drive. I'll just post that link here again. No deadline to fill the hackathon document necessarily. Obviously so the hackathon starts on the 9th. We'll probably call teams more or less final by kind of midday on Saturday. But obviously the sooner you can get your information in, the quicker people can start teaming up. But if you don't have an idea yet exactly, or you're not sure what you want to work on yet, then there's no specific deadline. But I would say if you are planning on participating in the hackathon and you do think you want to lead a project group, I would try to have your idea in that document by the end of the workshop this week. So by Sunday. So people can spend next week looking for teams. Yeah, that might have, the August 1st was probably a carryover from a previous template. That might have been a typo. So apologies if that was included in a message somewhere. the hackathon used to be right after the workshop, so the turnaround times for people finding groups was a lot tighter. But this year we have some time to get that all worked out before we start. Any other last minute questions before we sign off for the day? And stick around here for another minute or two, just in case somebody's furiously typing something before we log out. But if you don't have any other questions for today, then we will be in touch tomorrow.